Thank you. Good morning, Wrocław. Are you guys enjoying the conference? It's been amazing, isn't it? So many great speakers, but now you're stuck with me for the next half an hour. Sorry. So, what if I told you that your React Native application could start 2 seconds faster, while at the same time using 40 megabytes less memory? Would that be good? So, that is something that the Hermes JavaScript engine could do for you and for your users. Watch this video with me. Did you see the difference? Isn't it great? Hi, my name is Tzvetan, and I work on the Hermes team at Facebook. And I'm so happy to be here today and to be able to share with you the facets of the Hermes engine that can really help you improve your user's experience. So many of you probably already know what Hermes is. In fact, can I see a show of hands? Oh, that's great. Maybe I don't have to do the talk at all. But I did see someone in the back that didn't raise their hands. So this is for you, sir. So what is Hermes? Hermes is a brand new JavaScript engine developed for open source, focusing on mobile performance. It has been in production in Facebook for more than a year now, running most of our React Native apps on Android. And we have already seen significant benefits in startup performance, in application size, and in memory footprint. And we're hoping that you will find Hermes useful for your apps as well. Now, what do we really mean when we say it was designed for mobile? Well, it's simple. We're focusing on the devices that your users actually have. As engineers, we probably carry the latest flagship device. We have lots of CPU, memory, etc. But on the market, in reality, there are many Android phones that don't have the latest CPU, that have a little RAM, and have probably slow flash. And these are all factors that directly impact your user's experience. So that is what we want to optimize for. And we think that together we can make React Native apps even better. We have identified 3 important metrics for mobile apps. The first one is TTI, or time to interaction. This is literally the time between your user clicking on the icon and then being able to actually use your app. And users, unfortunately, are very impatient. I see this in my kids all the time. They click on an app, and then if it doesn't start, they move on. You don't want that to happen to your app. The next metric is the size of the binary that the users have to download from the application store. Or on Android, that's the APK size. And the last metric that we care about is memory footprint. Now, how much does Hermes really help with these metrics? We have measured one specific app on a Pixel phone, and note that we specifically chose Pixel because it's no longer flagship. So it improved startup performance by about half, application size was down by about half, and memory footprint was down 30%. So that's not bad. We believe that Hermes can bring similar improvements to your apps. If you want to try it yourself, we've tried to make it easy. Really, the biggest chunk of the work is to upgrade to a recent React Native version, anything after 60.1. And then it should be, in theory, only a couple of changes in the Gradle file. So please try it. Let us know what you like, what you don't like. We know it's not perfect, but I promise you we're working really hard on it every day to make it better. Now, I want everyone to better understand the philosophy behind Hermes. So I'm going to take you behind the curtain and I'm show you how it works on the inside. Open the black box, so to speak. Let's look at the execution pipeline of a modern JavaScript engine. Now, on the slide, we have two parts. On the left, we have build time. On the right, we have runtime. The left happens on your development computer, and the right is on your user's device. The right, whatever happens on the right side determines your TTI. Now, your development computer is probably very powerful. I hope it is. But you don't control the devices your users have. So ideally, you would want to move as much work as possible to the left side. So let's see what is happening here. We start with your JavaScript source. It was probably processed already by TypeScript, Babel, some packager thingy. And then you have to minify it. Minification helps both performance and size, so it's a good idea. And that minified artifact is what you are installing on your user's device. Now we're moving to runtime. When the user starts the app, React Native has to load this source and tell the JavaScript engine to execute it. But it cannot start executing right away. The JavaScript engine has to scan the entire source and locate in the source where every function is. So notice that even though it's not running anything yet, it already has to touch every character in the source, which takes both memory and size. Anyway, eventually it ends up with a table describing where every function is. And now it's ready, hopefully, to start executing. But before, it cannot run source directly. So now that it has to run that entry point, it goes, it scans it from the source, because now it knows where it is, and compiles it to bytecode. Because this is happening at runtime, there is not enough time, there is not enough memory, so this compilation process is not terribly, it does not produce terribly efficient bytecode, but it runs. So that bytecode is put somewhere in memory, and it's finally executed. And now we have our first function executing. That process keeps repeating, another function gets executed, and another, and eventually one of these functions will run 2, 3, 5, maybe 10 times. At the 10th time, the JavaScript engine is like, oh wait, this is an important function. Let's try to run it a little bit faster. And this is when it invokes the so-called baseline JIT. Now, the baseline JIT has to run under pretty severe constraints. It doesn't have memory, it doesn't have time, so it just takes every bytecode instruction and in a very simplistic process converts it to a few native instructions. It puts the resulting native code somewhere in memory. Now, that native code is huge. It is usually between 10 and 50 times larger than the original JavaScript function we started with. And it is probably about 3 to 5 times faster than the bytecode. Now, keep in mind what we have here. We already have 3 copies of the same thing. We have the source function that we started with, which is in memory. We have the bytecode, and we have this huge native blob. Anyway, it runs, and the process keeps repeating and repeating until eventually one of these functions will execute 100 times, or maybe 1,000 times. And this is when the JavaScript engine kicks in again. This must be a really important function. Let's make sure we really optimize it. And it finally initiates the high-tiered optimizing JIT. Now, you see how it was trying to avoid this and to postpone it till the very moment, till the very last moment, because this is a very expensive process. The optimizing JIT needs memory, needs CPU, so the engine did not want to use it until it was certain it had to. So the JIT runs, and it generates very efficient code. However, that code is only efficient because it has made certain assumptions about what is happening. Like, for example, that the parameters of a function can only be a number. When those assumptions get violated, the poor engine has to give up on everything and go back all the way to bytecode. And this process keeps repeating. Next time, when the same function gets executed 1,000 times again, it will have slightly different assumptions. Maybe they won't be violated. So this is a very, very clever process. Eventually, in the long term, it produces very efficient code. But the problem is that to get there, it needs both memory and time. And both of these things are a luxury that we don't necessarily have on mobile. So now let's compare this to the Hermes pipeline. Again, on the left, we have build time. On the right, we have runtime. And here it is. I think it's very easy to notice that we have moved almost all of the work in the left part. We want to do as much as possible on your laptop and not on your user's device. So let's go to the steps. We start with your source again, and Hermes doesn't really benefit from minification because it's a real compiler. We don't care whether there are comments on the source or how long the variable names are. So we take this whole source bundle and we compile it and we convert it to a special internal representation called SSA. Suffice it to know is that representation is very efficient for optimizations. So we use it and we optimize the whole bundle globally, all of your source. And we have time to do it and we have memory, so we try to do a really good job with it. Then when we have this optimized IR, internal representation, we generate bytecode instructions from it. And again, because we had all of this time and memory, the resulting bytecode is really tight and efficient. Finally, we take the bytecode, we take certain metadata, strings, this and that, and we produce a bytecode bundle. This bytecode bundle, first of all, is smaller than the minified JavaScript source by about 30%. But not only that, it was designed to be really cheap to load at runtime. This is what we ship to the user's phone. And at runtime, all that is left to do is to just memory map that bundle, which is a very cheap operation, and start running. There is nothing more. That's why Hermes is so fast on startup. Now, you probably noticed that there is no JIT in this picture. While in the other engine's pipeline, the JIT occupied like a significant chunk, there is no JIT in Hermes. And this was a deliberate choice. We found that in React Native, during startup, most functions are executed between 0 and 1 time. So the JIT just cannot help. It literally slows things down and eats memory during startup for no benefit. Now, even after startup, during the rest of the execution, we found that the JIT does not really improve the interactivity of a React Native app, of a typical React Native app. The JIT helps with things like expensive computations, long pieces of code doing transformations in memory, but that is not the workload of a typical React Native app. So it turns out that the bytecode execution gives you excellent interactivity with predictable performance and smaller footprint in memory. That's why we did it. So I mentioned a couple of times that the bundle, the bytecode bundle, has to be memory mapped. The question is this important? Should you even care about that? So let's look at what's happening here. We have the bytecode bundle, which is just a file somewhere in the flash storage on the phone. It contains the bytecode instructions for each JavaScript module, one after the other. We see foo, bar, buzz. I don't know how to read the last one. Cukes, maybe, I don't know. So then we memory map it. Memory mapping is basically telling the OS, create a virtual mapping of this file in memory, but don't read it yet. The file will be paged into memory on demand as we try to read each little piece from it. So let's say we then execute require foo When we do that, Hermes tries to read the bytecode instructions for the module foo in memory. And that's when the module actually gets paged in. Next, let's say that foo requires bar. Then bar gets paged into memory. And note that we didn't read the entire bundle. We only read these two modules, which saved us both memory and time. So this is already pretty good. And as you can see, this eliminates the need for technologies like RAM bundle, for example. But armed with this knowledge, you can actually tweak your app to start up even faster. It turns out that when reading from Flash, it is best to read sequentially. So if you happen to know the order, at least approximately, in which your modules will be loaded, you can change the order in the source file, like this. And now that order corresponds, hopefully, to the order that we need to load them. Then we memory map, and we require them one after the other. And this is literally the fastest and most efficient way you can load data from the Flash into memory, even from a slow Flash device. And this can make a difference. We have made other optimizations in order to make the bundle load even faster. For example, in a JavaScript engine, all property names need to be put in a global hash table. What we've done is we have stored the hash values of these names in the bundle. So when the bundle is loaded, we don't even need to read the strings themselves. The strings stay on disk, they don't even go to memory. We just read the hashes. So we just made sure that we do the minimal amount of work on startup. Something else that we've done is that we've arranged the different sections of the bundle in a way that makes logical sense so that they can be loaded sequentially. And sections that are not needed are put at the end, so they may never be loaded from disk. So even though you might be paying some cost for storage, at least you're not reading them. We have also done a lot to try to make the bundle smaller. And let's look at a couple of these optimizations. The first one is string deduplication. It should be pretty intuitive. When we have strings that overlap, we store them only once together, and then we use chunks of this big string whenever we need it. Another interesting optimization that we did is backtrace splitting. Now, in JavaScript, we're used to having an exception backtrace whenever there is an exception. It shows us the locations in source of every caller of the function that threw the exception. The problem is that this data, while very useful, also is significant. It takes a lot of space. So Hermes has an option that allows you to split that data into a separate source map. So now your bundle gets 25% smaller. When you get an exception, you don't actually get source locations of the callers. You get bytecode offsets. These are the offsets in the bytecode. But you can still convert them using the source map that we generated. And if you think about it, this makes perfect sense. Why should you ship what amounts to debug information to your users' phones? Now, I would like to dig a little bit deeper in some of the stages of the Hermes compiler so that you can get a little better idea of how it works internally. We start by parsing the source into what is called an AST, or an abstract syntax tree. By the way, for any of these stages on these slides, you can see what Hermes does for your own source if you run the command that I have provided on the slide. So I hope it's easy to see the correspondence between the example on the left, x equals a plus b multiplied by c, and the tree on the right. We have the assignment on the top, the plus, the a, multiplication, and so on. It is essentially the same thing as the original source, but it's just something that is easier for the compiler to operate with. And now when we have this tree in memory, it is a very good time to perform validations on it, like, is this identifier declared, and so on and so forth. Basically enforce the rules of the JavaScript language. After this comes really the most important part of the Hermes compiler, in my opinion. But I'm a compiler geek. So we are generating, from that tree, we're generating a static single assignment form, or SSA. This is a form that is used by all state-of-the-art compilers because it is really suitable for optimizations. And again, if you're curious, you can see what it looks for your own source. For our example, you can see what it looks like on the right. Without going into detail, the major difference is that it encodes a lot of information explicitly, and thus it makes it easy for the compiler to reason about your code and to optimize it. Now, having this representation, we perform a number of optimizations that I'm actually not going to go into, but something that is interesting and very relevant to React Native is the app-specific optimizations. So these are optimizations that are not just for any JavaScript source. They are designed specifically for patterns in React Native. And I believe that the possibilities here are endless because we are focusing only on this narrow domain. A simple optimization that we do, for example, is function name stripping. Now, you know that in JavaScript at runtime, you can get the name of every function. But it turns out that many React Native apps don't actually need that name. So why should we ship this name to your users' phones if it's not needed? Even when you minify the bundle, there are still names, even if they're short. But in Hermes, you can completely eliminate them. Again, this is optional, if you decide you need it for your app. Another interesting optimization is what we call static built-ins. So this optimization tells Hermes that certain library functions, like, for example, object.freeze, cannot be replaced at runtime. So when the compiler knows that something cannot be replaced, it can actually understand what it does, and it can reason much better about the code, producing smaller and faster bytecode. After we're done with all of the optimizations, we come to the fun part, generating the actual bytecode that the engine will run on the device. Again, if you're curious, you can see for your own source what it looks like. We basically take the optimized SSA that we have on the left, and we convert it to instructions on the right. If you're curious, the Hermes bytecode instructions are register-based, variable length. We have tried to use an encoding which is as small as possible, while at the same time fast to decode. And I've given two examples. One example is add R1, R2, R3, which means take the values of R2 and R3, add them, and store the result in register R1. And that instruction takes 4 bytes in memory. First is the code of the instruction, then the register numbers. Another instruction loads a constant into a register, takes 3 bytes. To gain a better intuitive understanding of this, here are a couple of examples of real functions that you might actually have. Well, I doubt you have these exact ones, but this one takes a parameter, adds 1 to the parameter. It uses these 2 instructions that we already saw, and it takes only 9 bytes in memory. The other one accesses a property, and it takes only 7 bytes. So I hope you can see that we've went to great lengths to make the bytecode very compact and efficient. And that's it. There are some links to our repository, to our documentation. I want to reiterate, please try Hermes. Let us know what you like, what you don't like, and I promise you we are listening. Thank you.